Today I'm going to explain about transfer learning. Okay, what is transfer learning, and especially how we can apply the transfer learning in the text analytics. Today, the agenda of the class are as follows. So you are going to learn what is transfer learning, and we're going to learn what is fine tuning. So we will check the fine tuning method and what is knowledge distillation, and then I will explain the current approach about fine tuning. It called at SPEFT, okay, parameter efficient fine tuning. And we will take a look what are the issues in the fine tuning and some approaches to handle those issues, such as LoRa, low rank adaptation. So this is not approximation, sorry. And the other is the QLoRa. It is the quantized LoRa. So this is adaptation. Yeah. So transfer learning. What is transfer learning? The deep learning. We learned already about deep learning. So deep learning shows remarkable success in various fields of artificial intelligence. And you already know also how we can apply the artificial intelligence with deep learning in NLP, in the natural language processing. So if it is related to vision, you can do with the object classification. If you do with the NLP, you can use the machine translation and etc. But it is very useful when you have a very large label dataset. So the key point is this one, the label dataset. And what if you have a new test? So what if you have a novel test? What does it mean by novel or new test? So for example, I have a text classification. Usually the text classification is about only checking whether it is spam or not spam. And then you also do the assignment to check whether the news is clickbait or not clickbait. What about if I want to have another kind of text? Let's say useful or not useful. So it is confusing and there is no label. There is no such annotation for this kind of useful and not useful data. So what if we do not have the label dataset? So we can do the transfer learning. Okay. Transfer learning aims to extract the knowledge from one or more sources. For example, we have the source task. Maybe we already have the data about text classification for spam or not spam. And we want to apply to a target task. So we already have the data about the text classification, whether it is a spam or not spam. And we want to transfer the knowledge to something about the class, whether it is useful or not useful. And we want to apply the transfer learning to get the knowledge. It means, if you have the traditional machine learning, maybe the text classification here, it is to check the spam or not spam. Spam or not spam. And then there will be another model to check whether it is clickbait or not clickbait. And you will have another task. So you will develop your own model, whether the model can detect whether the text is useful or not useful. So instead of doing with this traditional machine learning, so we can try to do something like this. We can collect the data from the spam or not spam. We can collect the data from clickbait and not clickbait, and then we combine those. and then we extract the knowledge from those two, and then we transfer. Okay? We transfer the knowledge into the new system. So the target task, which is the useful or not useful, can learn about the data and then use the transfer knowledge from the existing data. So that's the idea of the transfer learning. So why transfer learning in NLP? Yeah, because yeah, in NLP, yeah, there are many NLP tasks share common knowledge about language. For example, the linguistic representations. And yeah, we know there are some structural similarities. Yeah. Tasks can inform each other. For example, if we have the syntax, if we have the semantics, okay, so we can try to figure out the task. So if you, let's say, you want to do the text classification, yeah, and you do the sentiment analysis, yeah. Basically, yeah, the text classification is to classify the text. That's be spam or not spam. And then the sentiment analysis, you want to classify the text as well, whether it is positive or neutral or negative. So the semantic will be the same with the text for the sentiment. The syntax also will be the same to get the recognition for the sentiment analysis. But the only difference is, sometimes we only get the difference about the words, about the embeddings and etc. And meanwhile, some data may not have the label, and not that data is rare. Make use of as much supervision as available. So yeah, we are going to use another data set, or we are going to use another knowledge as much as possible for the another recognition or another detection. So empirically, transfer learning has resulted in SOTA. So I explain to you, SOTA means the state of the art. So state of the art is the recent technique, the recent approaches, the recent techniques. And yeah, it means the transfer learning has been performed well in the many supervised NLP tests. So for example, the task classification, the information extraction, Q&A, and etc. So based on this one, yeah, we will check more about the transfer learning. So the type of the transfer learning can be distinguished into this kind of diagram. So transfer learning, yeah, we can deal with the transfer learning on the same task. It means the label data only in source domain. Or we can do the transfer learning in the different tasks. So the label data in the target domain. Okay. So the same task means I want to transfer from the, let's say, the text classification from the source. And then I also have the text classification on the target. Okay. But maybe, yeah, the first one, we want to classify spam or not spam. And the other, I want to classify useful or not useful. So it will be different, but the structure might be the same. Yeah. So this also can be distinguished, okay, because this is the transductive transfer learning. So it can be distinguished into two. The first is different domain. We call it the domain adaptation, or different languages. We call it cross-lingual learning. Okay. So different domain means if I am in the university, okay, so the detection spam and not spam the text classification from the source about spam and not spam, it is only related to academic or because I'm in the university. But what about if I also need to do the spam and not spam related to company? Okay. So, it is different domain between the company and university. So we can apply the domain adaptation. So domain means what is the application field or what is the application domain. We call it this is domain. Okay. Because the one is university, the other is company. So it is different domain. But if it is the same university, let's say I have the data from the Hanguk WD, and then I also have the text classification from another university, let's say from Seoul National University. Okay, because they are still in the same university, then we can just say this is the transfer learning using the transductive transfer learning. Okay. The other is the different languages. So it means, if you have the text classification, spam, not spam using English. Okay. So you have the spam, not spam using English. And you want to detect the spam and not spam using Korean. Because maybe in Korea, it's difficult to detect the spam and not spam. So we want to get the data from the English data, and then we want to transfer it to Korean. Okay. And we need to use the method that is about cross-linguist learning. Okay. Or we can also use the inductive transfer learning. So the tasks learn simultaneously. So it means we will learn multiple tasks. Okay. So let's say I want to check the text classification. Okay, I want to check the text classification, whether it is spam or not spam. And at the same time, I want to also know about the name entity recognition. So it is multitask. So the first task is text classification, and the other task is NER, name entity recognition. So in the same model, we can apply to two different tasks. Or we can also do with the sequential transfer learning. So sequential transfer learning means I can do at the first is the text classification, spam and not spam. And then after I can classify spam and not spam, then I can classify to the next, which for example, Q&A. So the first task is text classification. And after I can classify it, then I can do the question and answer. Why these people send the message? Why these people send the spam message and etc. So by the definition on one paper from Pan et al. In 2010, there is a definition about domain and there is a definition about task. So we will take a look on this one. Domain means it is a pair of X and PX. X is a feature space and Px is a marginal distribution Px over the feature space. Task means a pair of Y. Y means the label space, and Py given X is the conditional distribution. So we can say this is the classification. Okay. So I know what is X, I know what is the features, and I want to predict Y. Okay. So this is from the Bayesian formula. Given that a source domain, we call it TS, and learning task TS. Okay. So S this means the source, and then T T means the target. So we have the target domain DT and the learning task TT. So the transfer learning aims to improve the learning of the target predictive function FT. So we have a function, and this function we are going to use the knowledge. What is the knowledge? We are going to use the knowledge from the domain in DS and the learning task TS. And the transfer learning, usually we have two conditions, whether it is not in the same domain for the source or target, or not the same task for the source and target. So what does it mean? Maybe we can see one with the examples. Okay. So this is the overview of different settings of transfer. We have the transfer learning. The transfer learning setting is this one. DS is not equal to DT. It means the source domain not equal to target domain, or the source task not equal to target task. So there are several scenarios depend on the detail setting. So if the task is the same, okay. So if the task is the same, yes, task is the same. What is the meaning by task is the same? Let's say we have the same task, text classification and text classification. So the text classification in the source and the text classification in the target. Okay. So if they are the same, then we need to check whether the domain is the same or not. If it is the same, okay, we can apply the traditional machine learning. In the traditional machine learning, we can learn about the knowledge distillation. So later we will learn about this one. And we can also learn about the semi-supervised learning. But if the domain is not equal, so if the domain is different, if source domain not equal to target domain, then we can use the transductive transfer learning. So we can use the domain adaptation. What about if the task is different? So let's say the first is the text classification, and the other, for the target, we want to use the name entity recognition. Then we need to check the Y. What is Y? Y is the label. So the label in the source, we want to check with the label in the target, whether they are observable or not. If it is observable, then we can do the inductive transfer learning. So some of them are multitask learning, continual learning. But if the label are not observable, so if we cannot get the label, then we can use the unsupervised transfer learning. So for example, we have the same task and the same domain. So if it is the same task and the same domain, then when the task and domain are the same, usually one can transfer knowledge for making the target model that are smaller, or we call it modular compression, but perform better than scratch learning. So scratch learning means you just perform with the data set, and then you perform the maybe semi-supervised learning or unsupervised learning, and then you do the prediction. So if you do with this one, then maybe the result is not better than the transfer learning. Okay. So maybe the transfer learning, if we can make a branch, so the other way is to do the transfer learning first. And then after we do the transfer learning, yeah, we can make the prediction. Usually this one perform better. Okay. So this is the way to use the knowledge transfer from the source model. One of the idea is the knowledge distillation. We will learn about this one. So make a target model mimic the source model and make the output or feature similar, and syntax and domains are the same. Following the source or the reference model is useful. So for example, I have one data set. I have one data set. This is about the maybe PU or popular person, for example, actor or singer and etc. And I want to do the person recognition. Okay. So maybe the first person is John, the second is Aaron, the third is Adam, and so on. I have another data set. Okay. So it is totally new, or maybe some data are intersection with the source data. And I also have the same task. This is person recognition. So the task is the same, and the domain is the same. So I use the picture as the domain. Then, yeah, in this case, we can perform the classical machine learning, the traditional machine learning. In the type 2, we have the same task, but the domain is different. We call this is the transductive transfer learning. The labels to predict are the same, but the input data samples are different. So since the tasks are the same, by learning the features invariant to source and the target domain, a target model can perform well. In many cases, the target domain datasets do not have sufficient labels. By learning domain invariant features, source model representation could be used for the target domain. So we call this is the domain adaptation. So we learn the representation that confuse source and target domain inputs, and learn the target representation that are similar to the source domain. Let's say, for example, you have this one. This is picture for digit. You know digit? Yeah. Digit is number. So this is digit by writing. So you write the numbers, and then we want to classify 0 until 9 digit classification. So 6, 2, 3, 8, 1, 10. Okay. The task is the same. I want to do the classification for digit classification, but now I have a new data. I have a new data about digit writing. So I want to classify this digit writing. So the domain is not the same. The domain is not the same because maybe this is the writing from British people, okay, or US people. And this is the writing from maybe Asian people. Okay. So the domain is a little bit different. Okay, we can say this is different domain. And the same task, we want to classify the digits. So this is what we call as the same task, but different domain. The type 3, we have the different tasks. Okay. And the different tasks, it can be distinguish into two, whether the domain is different or the domain is the same. So in the different tasks, different labels to predict. So when tasks are different, feature extractors and output layers are needed to be adjusted a lot for the new task. So here, with the same data, we want to first, I want to check the edge prediction. So in the image, we can do the edge prediction. Okay, the person is 31 years old. Maybe this person is 49 years old. This person is 34 years old, and so on. And the other task, I want to do the person recognition. So this guy is John. This guy is Aaron. This guy is Adam, and so on. So we call this kind of task from the same data, from the same domain. There will be different tasks. So the first task is its recognition, and the other task is person recognition. The second example, we have pictures, but the pictures is totally in the different domain. So maybe this is the picture about location. So many pictures are related to location, but the other picture is more about the scenery or object. So we want to do the first task is scene classification. Scene classification means I want to know where is the location. Okay, it is in the elevator, it is in the gas station, it is in the castle, it is in the cafeteria, it is in the cabin. But the other task is object classification. So we want to detect, okay, this is car, this is airplane, this is animal, panda, this is lion, this is guitar. So the task is different and the domain is also different. Okay. So this is the type 3. We have the different tasks. We can use the inductive or unsupervised classroom learning. Okay. We know there are several types of the classroom learning, and now I'm going to teach you the very basic approach for the classroom learning, which is fine-tuning. Okay. What is fine-tuning? So in the domain of NLP, okay, we know the source model pre-trained by large dataset. Source model means something that we already have and we already do the pre-train. So last week we learned about the pre-train model. For example, BERT is one of the pre-train model, and it is well generalized. So it is possible for using BERT to anything, such as we learned about the mass language modeling. Okay, so we learn about the MLM for BERT, and also we can do the next sentence prediction using BERT, and it can be generalized to anything. So one can expect it as a good feature extractor or a parameter initialization. Okay. The most important thing when you do this kind of learning with the word embedding, word to factor, is the parameter initialization. If you can do the parameter initialization better, then the learning result will be also good. Yeah. So to avoid overfitting, one can often freeze layers for small target dataset and can transfer to different domain and tasks, but using the same architectures, at least for the feature extraction part. So for example, if we have the big dataset, we can train using the deep learning. And after we have the model, we have the model until the last layer, So we can keep the weight in the last layer, and then at the end, the last we call this is there is an additional layer to do the fine tuning with the weight that we got from the source model. And yeah, the fine tuning will be done with the weight to predict the output. Yeah. So full fine tuning, okay, we call this is full fine tuning. The assumption for this fine tuning approach, features or parameters learned from some tasks are useful for another task. Okay. So this is assumption. So for example, yeah, I know that the source model is from BERT, okay, and BERT, it is good for the next sentence prediction, or we can use also for mass language modeling. And I want to check in the particular domain. So BERT is very general. It can be used for anything. But I want to do the next sentence prediction only related to the movie. So the target data, I use the movie data, and then I want to use the weight from the BERT, and I will like to transfer the knowledge from BERT into the movie dataset. So it is true in many artificial intelligence tasks, the lower level features of text such as ads. Okay, so it is good, but sometimes they fail to work. It can also fail. So when the data set of source and target tasks are very different. Okay. So maybe this is the same text. Okay. So let's say if I use BERT, and then for the target data, I use the movie data. Let's say the BERT, the BERT is using the English mostly, and then I want to do the next sentence prediction movie using the Indonesian language. Okay. Because it's totally different, then yeah, the transfer learning cannot work well. Or when the target tasks have no or very small label training data. So in this case, yeah, if we have a label data, the full fine tuning is good. But if the target data have very small label training data or no label training data, then it may fail to do the fine tuning. So you need to understand this kind of condition. So the full fine tuning means we need to do the selection. What is the pre-trained model that you want to use? Usually with the pre-trained model, we have the bias and the weight. Okay? So the pre-trained model, you can use any kind of pre-trained model. We have BERT. So we learn about GPT. Okay? When we already know about other kind of pre-trained models such as T5, BART, Roberta, and etc. Okay, so you can select what is the best pre-trained model, and then you can prepare the task specific dataset. So you can prepare, or let's say, okay, I want to do the sentiment analysis on the movie dataset. Yeah. On movie dataset, then okay. So once you prepare the task specific dataset, you can do the fine tune. Okay. Fine tune means you pass forward the weight. So if we have the LRM or we have the weight, okay, so we pass the weight into the task specific dataset. So we fine tune it. So the fine tune is another neural network. And then after we do the back propagation, backward pass, so we have the feed forward, backward, feed forward, backward, feed forward, backward until it is converged. Then at the last one, we can get the final updates or the final model. So the backpropagation, it means with updates according to the loss function. And at the end, until the weight converts, so the final model will be ready to be used in the real world application. So let's see example, with a very small example. In this case, I have the word I like cats. So the sentence embedding, I can just make very simple one with the ordinal. Let's say 1, 2, and 3. 1 represent I, 2 represent like, and 3 represent cats. So let's assume that the pre-trained weight, so this is the weight that we got from the pre-trained model. So usually the pre-trained weight is very huge, but let me just use very simple to give a simple example. So the pre-trained weights, or we call it the hidden layer, or sometimes we call it the initial layer, that's this one. And then we have the bias. So we have the weight plus bias. Usually, this is for the neural network task. And the task specific data set, or we call it the fine-tuning target. For example, I have the adjusted label for the binary classification Y. So one of the target example is Y 0, 1. Okay, so it's binary classification. Now, I need to do the forward pass. Okay. What is the meaning by forward pass? So in the forward pass, I will do the if you know the deep learning, we use the feed forward neural network. It means we feed the data, we feed the data into the weight from the pre-trained model and also plus the bias. So the data that we have, which is I like cats, okay, this is just for example. Let's assume that this number represent I, the one that we learned before. Like, it is 2, and then cats, it is 3. Okay. So I have 1, 2, and 3, and then we have the weight transpose plus the bias. Okay. The weight transpose, this is the weight that we already look at the numbers in the previous slide, and we did the transpose plus the bias. This is the bias. Then we can just do with the matrix multiplication. So 1 multiply by this one transpose, it means 0 0.1, 0 0.2, 0 0.3, and then we have 0 0.4, 0 0.5, 0 0.6, and then we have 1, 2, 3. Then you can do the multiplication. 1 multiply by 0 0.1, okay, and then 2 multiply by 0 0.2, and 3 multiply by 0 0.3. For the next, we can do also the multiplication. 1 multiply 0 0.4, 2 multiply 0 0.5, and 3 multiply 0 0.6. And the result of this one will be added with the bias. So here 1 multiply 0 0.1 is 0 0.1, plus 2 multiply 0 0.2 is 0 0.2, 0 0.4, plus 3 multiply 0 0.3, so it is 0 0.9. Okay. 0 0.9 plus 0 0.1, this is 1, plus 0 0.4, it is 1.3. 1.3 plus 0 0.1, so it is 1.4. Okay. And the same with this one. When you do the multiplication and the summation plus 0.2, then the result will be 3.2. So we get the weighted sum z equals to 1.4, 3.2. Whenever we do the neural network, we need to also calculate the activation function. Okay, so let's use the softmax activation function with this formula. So E, yeah, is a function power of xi divided by sigma E power z. So we have the softmax of the value 1.4 and 3,2, like this one. So we can just fit into this matrix. It means I would like to do the E power of xi. Xi is 1.4 divided by the sigma of Ez. The sigma of Ez means E power 1.4 plus E power 3.2. This is for when I equals to 1. Okay. And I equals to 2, we want to calculate this one. So E power of 3.2 divided by E power 1.4 plus E power 3.2. So if you calculate with your calculator, you will get the value 0.14, 0.86. Okay. So yeah, I think I need to check. I need to open the calculator. Let me show you. Oh, I think I need to share my screen. Okay, so you can see we have the E. Okay. Oh, yeah, E is learn something. Okay. So we have the E power 1.4. Okay, so the result is 4.05. Okay, 4.05 divided by 4.05 plus, this is the same, E power 1.4 is 4.055, just 4.05 plus E power 3.2. Okay, and then oh sorry, maybe this is not correct. 4.055 divided by 4.055 plus E power 3.2. Okay, so we get the value 0.14. Okay, so let me just use 0.14. So you can use also the same with the second cell. This is E power 3.2 divided by E power 1.4 plus E power 3.2. So the result will be this value. Okay. And then we need to calculate the loss function. the loss function means, we will use this loss function to update the weights later. So the loss function, in this case, we just use the cross entropy. Okay? If you know about the cross entropy, we can use the log like this formula, yi multiplied by the log y hat I. So y hat I is the prediction. Yi is the actual, the actual value from the target 0 and 1, and y hat I is the prediction. Okay. So we can calculate this one by using the log function. Okay. Using the log function, we have the 0 multiplied by log 0.14. Okay, so 0 multiplied by log 0.14, and then 1 multiplied by log 0.86. Okay. So the result is the log function. It will give you negative if log 1 it is 0, and if it is lower than 1, if it is lower than 1, it will be negative. If it is higher than 1, it will be positive. Okay, so you can check later. And the result is 0.15 negative, and then we have the negative. So negative and negative, we will get the positive. So this is the loss function for this data. Yeah, if you, I give you some hint here. Usually in the in the code that you use in the Python, they use the natural logarithm. Okay. So the natural logarithm means this one. You can see log 0.86. Okay. 0.86 log. Okay. So you can get the 0.06. So this is log base 10. Okay. Log base 10. And usually we, in the major function, in the major loss function, it use the natural logarithm. Natural logarithm means you can use the learn function. Okay, the learn function. Okay. You can see this one 0.86, and then you want to calculate learn function. So you can get the value is minus 0.15. So this is the learn function or the natural logarithm. Okay, so yeah, in the final exam, I will give you problem like this one. You need to calculate the loss function. Okay, so the loss function, it means we use the natural logarithm learn function instead of log, even though this is log. Okay, but you can use the function from the calculator with the learn. Okay, okay let me stop here. Let's have a break. Okay, I will continue after the break.